This is a lesson on degrees of freedom and how equipartition theorem relates to kinetic theory in the heat and thermodynamics unit. In a prior lesson, I had introduced kinetic theory, but at the most basic level with monatomic molecules. Okay, so that the degrees of freedom were the lowest as possible. It's the simplest model to think about kinetic theory. But at the time, I had mentioned that there was a more proper model talking about degrees of freedom. So let's go into that topic a little bit more in depth. Degrees of freedom reference each independent possible dimension of motion. And you can see over to the side, I put some visual representations of different types of molecules so that we can look through at their possible dimensions of motion. Okay, when I think about a simple, just an atom, this might be an atom, right? Just flying through the air. I know that it can have translational, like kinetic energy. It can move in along a line with some velocity. And when I look at that velocity, remember we're looking at dimensions of motion. And it with just velocity, we can see that it can move in three space. It has an x velocity, a y velocity, and a z velocity. Okay, so according to degrees of freedom in translation, there's 3 degrees of freedom there in each dimension, x, y, and z. When we look at larger molecules, if we go past atoms to some sort of larger molecule that has a composite, all right, we can look at the rotation of that molecule. And at this point, you should have studied rotational motion and moment of inertia and rotational, maybe kinetic energy. And you can imagine when I think about this diatomic molecule, you can see that there's 2 atoms here. There's symmetry around this axis that I'll draw. I'll call it the x-axis. There's symmetry around it, and so there's no like moment of inertia or rotational kinetic energy around that. But if I draw the other 2 axes in here, I can see that there's some sort of moment of inertia and some sort of rotational kinetic energy going on there for this diatomic molecule. If I look at a more complex molecule and notice that this is a linear molecule as opposed to this being nonlinear, I went out and this is water, right? This is a water molecule, right? When I look at this and I look at the 3 dimensions along which it can rotate, I'm going to have a moment of inertia and some sort of rotational kinetic energy in 3 dimensions, all right? So here with rotation, we could have 2 to 3 independent possible dimensions of motion for rotation, okay? The last possible place that we can look for degrees of freedom is vibration. And the model that I picked out over here, you may or may have not covered spring motion, springs, and we know that molecules or any sort of things attached with springs within solids, that's how we think about it, is that the molecules inside are separated by springs. Or if you're looking at these molecules, if I think about this atom and this atom, we think of it being attached with a spring in between. There's some springs between these atoms and the water molecule. We can think of a spring here, and we can think of a spring here connecting those atoms. This is ammonia. All right, it's a NH3. You can see that there's 3 atoms in here. There's those 2, the nitrogen. We have 2 hydrogens you can see in the front here. And you can see that the number of springs in this molecule is dependent upon the number of atoms in that molecule. Okay, so it depends on n number of atoms in the molecule. And what happens is the spring between those sort of contain the energy of those 2 molecules vibrating relative to one another. So this is what we call the vibrational energy. And you can imagine that if I apply a set of axes to this situation, we can have vibration in the x dimension, we can have vibration in the y dimension, and we can have vibration in the z direction. So not only do we have 3 dimensions here, but we have 3 per number of atoms, and then there's some duplicity because we can't double count atoms, etc. Okay, but the larger idea is these are the 3 independent possible dimensions of motion. Is there's translation, rotation, and vibration, and we have 3 dimensions each there. In summary, when you actually want to count degrees of freedom, the important considerations for any general polyatomic molecule with n number of atoms is that there's always 3 translational degrees of freedom. You're always going to get degrees of freedom of 3 there. We need to consider if you're doing rotation, whether there's 2 or 3, whether the molecule is linear or non-linear. And vibrationally, if it's a linear molecule, we have 3 dimensions per n number of molecules minus that factor of duplicity that I was talking about. And so linear, there's a -5, and non-linear, there's a -6. And all of this actually is dependent upon temperature. This goes into a little bit of theory that we haven't gotten to, quantum theory and available vibrational states in an atom. So I'm not going to go into detail there, and I will say for the intents and purposes, if you're in a course with me at this moment, we're just going to look at mostly monatomic and diatomic gases at what I'm going to call ordinary temperatures, all right? So ordinary on the face of the planet temperatures that you might experience every day. Okay, I'm going to note again, some places I've seen have called degrees of freedom D. Other places I've seen have referred to the degrees of freedom as F. I refer to it as DF for degrees of freedom. So hopefully that alleviates any confusion you see in notation. The last thing I wanted to point out here on this slide is that when we get to equipartition, which is the next thing I'm going to talk about, they talk about the specific heat of different molecules. And specific heat has to do with equipartition and dimensions of possible motion, and that relates to specific heat. So when they look at that, I like this because it relates that to the temperature. So as temperature increases, we can see that at low temperatures, I'm going to tell you that this is a graph for hydrogen gas. Okay. And you know this to be a linear diatomic molecule. Okay. So there's a hydrogen, and it's linear, right? It's diatomic. So at regular temperatures here, in the middle of this graph, I'm going to say regular temperatures. If I take Kelvin and I add it, to 0 and to 100, or even, if you're looking in engines or something like that, some sort of hot space where we use hydrogen gas. In here, it's 5/2 R. And what we're really looking at is this 5 in here. We're going to have 3 degrees of translation, and we're going to have 2 degrees of rotation. All right. This thing can move in 3 different dimensions. All right. And then it can also rotate. So we're going to have some rotation this way, and we're going to have some rotation this way. So overall, that equals 5 degrees of freedom. It turns out if you're in the lower temperatures, what happens is that there's no rotation. We're getting a little bit, right? We're reducing the energy of that molecule so much that it starts not moving in typical ways that we would expect. And so it can only translate. When we get into higher temperatures, what we see is that there's actually some sort of, instead of representing the bond in here with a line, I'm going to represent it with a spring. So at higher temperatures, we're going to get this addition due to 2 vibration, right? There's a vibration of one molecule and a vibration of the other molecule, so you get a factor of 2 there overall. So you're going to have the factor of 3 from translation, the factor of 2 from vibration, and you're going to have from rotation, and the factor of 2 from vibration. So overall, you can see that's the 7 in there. So counting degrees of freedom is a little bit, there's a couple of different important considerations that you need to take into effect. And then I am going to say on top of all of this, this is not an exact science. what I've seen in different sources as I went through preparing this lesson, that you can actually like measure the specific heat of an object and then do some calculations to find the degrees of freedom, and it turns out to be very odd degrees of freedom, close to what we expect theoretically, but not exactly. And again, it has to go back to this vibration and rotation, what temperature they're at, and then the energy within that atom, what's available, and is if that atom is taking up those energy states. Okay, so simply overall, I will emphasize that for most of the applications that I have in my courses, we'll look at monatomic and diatomic gases. Okay, so when I go back to kinetic theory and I bring in this idea of equipartition, so that's the other other piece I want to put into your knowledge base here, is what equipartition says. Equipartition says, and you may see it from the word if you're good at dividing up words, equi and then part, we have equal parts. The energy of a system, and here we're mostly looking at like a thermodynamic system with heat and temperature, pressure, volume, etc. The energy of a system is equally distributed over its degrees of freedom. So you can see how it's important to count up your degrees of freedom. Okay, and what I mentioned on the previous slide is that equipartition has implications in any study of energy. So they were looking at the specific heat capacity, and then also the study of energy with kinetic theory, when we're looking at molecules and how much kinetic energy a molecule has dependent upon its temperature is also dependent upon those degrees of freedom. If the energy is equally distributed over its degrees of freedom, then we can relate the kinetic energy to the degrees of freedom. Okay, so that's the theory in there. Again, monatomic will be 3 and diatomic will be 5 for the most part. So you can bring that a little bit of addendum into your problem solving as you're looking at kinetic theory problems. I picked out an example for us, the speed of oxygen gas. When I look at oxygen gas, I have 2 oxygen molecules. All right. And notice that we're at more of a normal temperature on the planet. We're not less than like, they say maybe 60 Kelvin. They say like the low end is 60 Kelvin. And then the high end, we're getting into like 2000 Kelvin. Like anything above 2000 Kelvin will be the high end. So you can see that we're at a very normal temperature. For a human being, we don't like the temperature of 300, but it's a very normal temperature for oxygen. Okay. This is asking, what is the RMS speed of an oxygen molecule gas at 300 degrees Celsius? Okay. So there's a few things going on here. When I use kinetic theory, I know the temperature needs to be in Kelvin, so I can convert that 300 degrees to Kelvin, and that will give me the Kelvin. What else is going on here? I need the Boltzmann constant. That's something that you may have memorized by this point in time. 1.38 times 10 to the negative 23rd joules per Kelvin. Remember, this is sort of why we have to use Kelvin, or a reminder that we have to use Kelvin, because our constant is in Kelvin. When we're looking at RMS speed, we're going to look at 1/2 mv squared. So when I'm looking at this equation, I'm just filling out the parts here that I need. I need a mass. I'm going to remember the mass of oxygen is 16 atomic mass units. So that means O2 is 32 atomic mass units, or 32 U's. You may see this referred to as U's. I call it AMU's to remind me that it's atomic mass units. And I'm going to remember that one atomic mass unit is 1.66 times 10 to the negative 27th kilograms. Okay. The last thing I need to identify here is the degrees of freedom. Again, we have a diatomic molecule at a normal temperature, so the degrees of freedom is going to be 5. So I'm going to put all my pieces together. I'm going to solve for velocity. The velocity here, velocity, I'm going to move, let's see. The half cancels on both sides. That's great. I love when halves cancel. We have a 5. And then a K and a T on the top. Degrees of freedom is 5. We have a K and a T. If I divide by M and then take the square root, I'll get the velocity by itself. So plugging these numbers through your calculator, I'll write them out here so you can see how it goes. I'm just going to leave this as 300 plus 273.15 if you like decimals. And then divide by the mass is going to be 32 times 1.66 times 10 to the negative 27th. And then I'm going to square root it. We have a lot of really small numbers going on, 10 to the negative 23rd and 10 to the negative 27th. That's 10 to the 4th, and then we square root it. So I'm thinking my velocity is going to be in the hundreds somewhere. And when you run this through your calculator, that is indeed true. You're going to get a velocity of 862.84. And we're going to remember, since we have everything in SI appropriately as we are expected to do, our units will come out as meters per second. So just looking at, in review, when you're using kinetic theory in light of equipartition and degrees of freedom, make sure you're considering what molecule or atom you have. Atoms are monatomic. They'll have 3 degrees of freedom. Diatomics will have 5. Larger polyatomic molecules, if you happen to get there, usually they have 6. Sometimes they have 7. It depends on if the the molecule is linear or non-linear. So again, going back to that slide, those important considerations, if it's linear or non-linear, and the temperature of it all. You saw that was a factor. So good luck and enjoy the material.